Problem 10 is another example of graphing a system of linear inequalities in two variables, determining the feasible region, finding the corner points of that feasible region, and then evaluating some objective function at those corner point values to find which corner point maximizes the objective function and which corner point minimizes the objective function. Just as we did in problem 9, the first thing we must do is graph the inequalities that are our constraints. We also had non-negative conditions which told us that we were only in the first quadrant. The x's had to be greater than or equal to 0, the y's had to be greater than or equal to 0. Remember, to graph a linear inequality in two variables, we first graph the equation. So we're going to graph these two equations. That will establish our line for us, and then we will shade whichever is the appropriate side of the line for the inequality we have. Let's get our intercepts again. Let's let x be 0, and then we'll let y be 0 to get our two intercepts. If x is 0, doesn't y have to be 12 to make 24 on the left side? Or if y is 0, would x have to be 8? So I have the point 0, 12. And I have the point 8, 0. So here's my line. And I want the values to make it greater than 24. Well, if x and y were 0, that would be not greater than 24, so it must be this side of the line that contains the points that solve that inequality. All right, now, getting the intercepts here. And we'll let x be 0. We'll let y be 0 to get the two intercepts. If x is 0, then y is going to be 9, isn't it? 4 times 9 will be 36. Or if y is 0, x would have to be 12. So we have 0, 9. And we have 12, 0. So here's our line for that equation. And now we want the ordered pairs that will make that less than 36, which would end up being the ordered pairs here below the line. And so our feasible region is this small sliver right here that's bounded by the corner point 8, 0, the corner point 12, 0, and this corner point, which is unknown. But again, it's the corner point that's formed by the intersection of the two lines. So that's the point that's the common solution for those two equations. So if I solve this system of linear equations in two variables, if I solve that system, I will find that solution point, which will be the third and final corner point of my feasible region. So let's take this first equation, multiply it by -1. That'll give me negative 3x minus 2y equals negative 24. 0. So 2y equals 12, so y equals 6. So now we know the y value of that ordered pair is 6. And if we take 6 for y, let's take 6 for y, put it back into this equation. 2 times 6 would be 12. So that means this quantity has to be 12, so 12 plus 12 would make 24. If this quantity has to be 12, x has to be 4. And my remaining corner point of my feasible region is the corner point 4, 6. And so now I'll evaluate my objective function at each of those corner points, because it's at the corner points that the minimum and maximum value of the objective function occurs. So 8 times 8 will make 64. 3 times 0 won't be anything contributing to it, so it's 64. The objective function's value is 64 when the corner point is 8, 0. At the corner point 12, 0, 8 times 12, let's see, what is that, 96? 8 times 10 is 80, 2 times 8 is 16, 16 and 80 is 96. And how about here? 4 times 8 is 32, and 3 times 6 is 18. 4 times 8 is 32, 3 times 6 is 18, that's a value of 50 for the objective function. So the maximum value of the objective function is 96, and it occurs at the point 12, 0. The minimum value of the objective function is 50, and it occurs at the point 4, 6.